Hi, everyone. I am Edgar, and I'll be talking a little bit about what, well, it's not specifically what my research is, but it's like the general theme of what I'm doing here. For context, or just to give a quick introduction, I'm an MIT grad student. I'm in the same program as Angelo, the first doc from yesterday, and it's CPP, Technology and Policy, and I'm doing a dual degree also with EECS, that is Electrical Engineering and Computer Science. So this is the outline for today. I'm going to talk a little bit about like my personal and academic journey, then kind of for me, why I am doing what I'm doing, that is that I realized this revolution of electric and autonomous vehicles. And then we're going to go a little bit more in depth regarding how these autonomous vehicles, like the tools that we use for these autonomous vehicles and the possible impacts that they have. Talking about a little bit about the reinforcement learning. It's a ML approach, but we didn't touch this during our course. This is a little bit more advanced. And then I'm going to talk about adoption pathways for autonomous vehicles. And then I'm going to conclude with some takeaways and warnings and final messages. So a little bit of my academic journey and personal journey. And I put this in like two kind of transitions. One is like a field transition. I started my undergrad in mechatronics. Then I switched major to physics and I had to transfer school. Then when I was like finishing my undergrad, I did a research internship in Berkeley, and I was in the California Institute for Energy and Environment, and it was more like CS, data science stuff, but it was like very, very exciting. So I kind of liked the approach of like not only the technology, but how it interacts with like different systems and societies, and like the multi-dimensional impacts that like the technology can have. So that was like more energy. And then I came to MIT thinking that all I would do was energy. And it's very exciting here. There are a lot of energy folks. Actually, most of my program, and Angelo can affirm this, most of them I think are in energy. And there are some very interesting energy projects happening here. But I actually ended up working in transportation, and this journey for me has been like pretty kind of exciting because I realized this amazing field. And yeah, the objective for today is kind of share what I just realized. Then in terms of the approach, I would say that I started like in mechatronics from like, oh, I want to do things. I want to build things. I didn't know exactly what kind of contribution I want to make, but I knew that, oh, I want like hands-on thing. And so when I was in mechatronics, I was like more like technical and I would say like applied. Then when I switched to physics, I switched because I remember the first year in my undergrad, I was like, oh, when like for the physics classes or electronics or any class, I was like asking them more fundamental questions of like, oh, wait, but where does this formula come from or something like this? So I switched to that, and now I'm all about like implementation. So I'm in this kind of intersection between technology and society. So, okay, there's people like developing the tools, but how do we actually use them? How do we use them in a good way? And it's very related to what we touched last week in terms of algorithmic bias and how to use these types of technology responsibly. And yeah, I'm currently in two labs, the Laboratory for Information and Decision Systems and the Institute for Data Systems and Society here at MIT. So if you're curious, you can search these labs, and there are very interesting projects happening. Mm-hmm. So let's go to reinforcement learning. And with this, what is reinforcement learning? So we have, well, maybe a quick question. what do you guys think when you hear reinforcement learning? I don't know if anyone's familiar with the term. So if you are, please share it in the chat. Yeah, what comes to mind when you hear reinforcement learning? What is a reinforcement? Usually we talk about like reinforcement loops in like engineering, and the fact that it's a loop already kind of tells you something. What comes to mind with that? Conditioning, yeah, kind of. The important concept here is a feedback. We have a feedback. So we saw during these 2 weeks, well, the part of the course that we've already done, different machine learning algorithms for, let's say, classification and regression and like trying to predict something. But when we are trying to learn an optimal behavior based a couple of like an environment and make decisions, there's always something like, you can think about this from how do you teach a child how to behave, no? And you can basically teach this baby that is just new to the world. Oh, if you do this, this has like good consequences or bad consequences. So this part of information is how we learn. And we are basically applying that concept just to machines. And for this, we're designing a metric. So there's an environment and there's like a clear goal with rewards and punishments. So, and in general, this feedback loop goes to like, oh, we have an agent, and this agent is changing our environment, and it's interacting with our environment by doing an action, and this action kind of changes the environment, and there's a reward from that environment, and also a change in the state of the environment. But this part is important, the reward, because this is a feedback loop. So how, maybe this is a little abstract, but this is how we, for example, we train machines to play games. And these are different like steps in the iteration. I think this is like one of the starting values, the one that you see on the right side, on the left side. And here is like, oh, we in like halfway through the training, and then once like this program mastered this game. So what you can see here is that with this game, the starting position of this little bar where the ball bounces is just like trying different things, and it's initializing its position and playing like, oh, without moving. And then based on the things that our algorithm or our game allow the agent to do, so the kind of actions that in this game would be, oh, to move horizontally. Based on this, it's playing, you know. So it's playing, and eventually it learns like, oh, it needs to bounce so that I can crash most of these blocks. And it's basically learning that. And here the reward or the punishment is like, oh, you have this score, and this is better than the one you had previously, or worse, etc. So you can learn it this way. Mm-hmm. And this is not only for games. Here's the training of another game. As you can see here, it's starting with like a fixed position, and eventually it's kind of learning how to learn. It's learning how to play, sorry. So, but this is not only for games. What other kind of environment do you think these could be helpful for? What did you use this approach for? Let's think about it a little bit. We're talking here about making decisions. Okay, car simulations. That is a big one. We have like all autonomous vehicles are trained using this reinforcement learning. And I would extend this to like when we want to make any decisions, we use reinforcement learning. When we don't want to like only like classify or predict something, but interact with the real world, and where there's a clear kind of environment, and we are changing our environment based on like our decisions. Usually, the environment or whatever we want to do, because we are optimizing our algorithm for something. So we can make this metric, and for example, when we have like this supply chain, or these robots that are like taking in the industry, taking our objects and moving them across the factory, etc. And like you need to like carry the object without or just like classify and then put it in the right position, etc. So we can define a reward, or if it's working well, or a punishment if not. So in general, there are for like decisions, and for when we want our machine learning or our agent to interact with the real world and a real environment. Mm-hmm. So now moving on to how this applies to transportation. Here in my lab, what they do, it's reinforcement learning, and it's called Lagrangian congestion mitigation. And what this basically means is that you have, imagine in the future, we have a certain number of autonomous vehicles on the road. And we basically, if we can control these autonomous vehicles from a centralized source, we can basically optimize the flow for the entire system. And this is a project I'm currently working on. This is the non-stop intersection eco driving model. And what this basically does, this is an optimization, a flow optimization algorithm. Well, not an algorithm, but a whole system. And it's using reinforcement learning. So what we want to do here is that, knowing that the cars emit more CO2, that it's harmful for us and the environment, we are basically asking the question of like, oh, what if we're able to replace the traffic lights with just a smart management of these vehicles? So, and what if vehicles no longer need to stop, like to hard stop there and then to start again, because this emits more. And this is basically what the optimization, the final optimization look like. If you see here, they're slowing down as they're approaching the intersection, but they're not hard braking here. Mm-hmm. So these and other optimization flow approaches are being studied. And with this, there's then the question, this is like more technical. And now what I'm like, this type of exercises and studies have been present here in my lab for the last, like, I don't know, 5 to 10 years. But then the question, as we are more and more capable and we see these actually being implemented, that question is, okay, what's the direction of this technology? How can we implement this? And this is, to be honest, what I'm more excited and like more interested about, in like, yeah, what's the direction of this technology? So an important concept here is the adoption pathways, and it's basically this direction. So for reference, when there are different studies that analyze how was the diffusion model for technology adoption, and it seems like it's an S-shaped curve, as you can see here, similar to the one we saw for the logistic regression. This is not probability; they just have an S-shape, both of them. So it's not the same. And this is the cumulative adoption. And what we can see is that at the beginning, it's like a slow adoption, and as time passes by and there are like different changes, They start with like the innovators, and then the early adopters, and then the early majority, then the light majority, and the laggards. So this can be explained, and this is more into like the technical side of how technology is adopted and implemented by dynamic processes. That is like learning by doing. That it's basically that the technology decreases the production cost over time because they're learning how to do it more efficiently. Then there are something that's called network externalities that basically are the benefits of using the technology increase with a number of users. You could think about, WhatsApp or something, that you wouldn't use it, or it's more valuable when more people are using them. So you kind of see this behavior. And in general, the product is more valuable over time. That's what accelerates the adoption as a reinforcement loop. So what's happening here is a reinforcing loop that it's accelerating the adoption. And yeah, and basically for autonomous vehicles, we have, it's kind of, there are a lot of details on this, but I'm gonna give you like the super simple model for like the two extreme possible directions that this technology could take. So one is the shared and on-demand mobility. And one example for this is I don't know if you guys know this company called Waymo, but they're owned by Alphabet, the same owner as Google. And they basically doing a robot taxi model that it's on demand, like an Uber, but without the drivers. And here, just to think about the societal implications of this, each autonomous vehicle can fulfill the mobility needs for multiple users if managed effectively. What happens here is that, in general, that the demand for travel is reduced. And these kind of self-drive cars displace self-owners. So there are less vehicles on the road. And these kind of directly reduces the externalities that transportation has, like pollution, congestion, greenhouse gas emissions. And not only that is like less demand, but the vehicles that remain on the road can be optimized if they're controlled by a centralized source. So they can, as we saw here, they can do these kind of things. Maybe not as efficient as this one, but the vehicles on the roads could do some optimization. And with a widespread adoption of kind of this technology, we can unlock wasted space that's currently used for parking. There's a study that says like, more than 90% of the time for all of our individually owned vehicles it's just wasting parking space somewhere because they're usually parked. And we need a lot of space for that. And with autonomous vehicles, we can have our parking slot like very far, and we need like less vehicles in general. So these can fundamentally change the mobility patterns. So this is a very good scenario for autonomous vehicles. However, there's the other side of the spectrum, that it's the individual ownership model. And for this, and this kind of works more related to this S-shaped curve. Why? Because journeys in general become more convenient. Users are willing to travel more and farther away. And this raises the overall demand for cars and travel in general. And the thing is, like, the early adopters here are the ones that can afford this, and the ones that can use like that time to like work. And if the autonomous vehicles is driving for you, you don't care like to travel farther away, and to just are more willing to stay in traffic. No, but what happens here is that the demand basically increases. So increases the congestion and the fuel consumption, the greenhouse gas emission, they all increase. And moreover, even worse, car manufacturers want to sell as much as possible. So they are kind of pushing in this direction. So there's this big warning here that without any intervention, because of this behavior of how technologies are adopted and the multiple benefits, individual benefits that autonomous vehicles bring to the general user, without the intervention, a private ownership model for AVs is expected to prevail in the long run. And unfortunately, the current initiatives, I'm meaning like the policy frameworks for this, and the set of incentives, etc., um, are not going in the right direction. So just to conclude, the takeaways here is that technology is super powerful. It can shape our society. Naively, it's assumed that autonomous vehicles can bring benefits. This is all working from it's based on reinforcement learning, but however, the societal impacts are highly dependent on the adoption pathways. So we need to be careful about, oh, this is a very exciting technology, but how is it rolled out to society? Mm-hmm. So thank you guys. If you have any questions, feel free to ask me, and I'll also leave my email in case you want to reach out.